All right. So happy Tuesday. As you can see, we've displayed our message. Uh, defined our variable message Happy Tuesday, appended a line feed and a null. So that's the premise for today's lectures. We're going to be talking about printing statements. So we hit record. Yep. Before we start, I do want to touch up on a few topics just very shortly. Does that say assignment 9? Yes, we'll get to that really shortly. But let's go ahead and talk about Twitch in general as a platform, because since this is an open platform, we are susceptible to having people outside of our enrolled class list join in our lectures, and that's perfectly fine. I'm open if anyone wants to watch the lectures and learn a little bit. Perfectly fine. There was someone being a little bit disruptive during yesterday's lecture in session 2. So just want to bring it up. If that ever happens, I'll just probably just time them out so they can still learn and watch lectures. We do get some VBots here and there sometimes, so I'll go ahead and ban them as well. But hopefully those minor load disturbances isn't too bad for you guys. Let's go ahead and talk about late homework. So a lot of you guys like to turn in homework late for some reason. I know sometimes it might be due to an internet problem, or sometimes you just need extra days to finish it. Whatever the case is, I think what I'll do is I'll amend the policy just a tiny bit. I will allow you guys to submit your homeworks and your tests. I'll say for now, let's do 2 days late. So any solutions that we provide, probably I'll go over them later within like 2 days or so. But I'll take off maybe, let's say, 10% for each day, up to a maximum of 2 days, except for the last assignment, because grades are due, I think either like 1 or 2 days after the semester ends. So that does not give me or my TAs enough time to grade whatever assignments or quiz or whatever. So the caveat is the last one you must turn in on time. There's no exceptions there, just because I have to turn in grades. Let's go ahead and talk about grading and points. So remember the syllabus, we said something along the lines of, all right, let's pull it up. In terms of grading, where is it? Right here. So homework's worth 45% grade, quiz is worth 10, and then each test is worth 15 for a total of 100. So the way that works is the homework total. So all of these are just based on a point system. Homework is worth 450 points, quiz is 100, and then each test is worth 150. So if you want to do the math there, that's how that adds up to 100%. Okay. Now I say that because on some of these assignments / quizzes, I might just move around some points. So as you can see, I did post assignments 4A. It's in the form of a quiz, but it'll be added towards the homework / assignment grade. So it's 20 points. We'll go over a little bit more into detail what you have to do, but here's just a quick preface. You don't have to write an assembly file, but you will have to write a function in assembly, just like you did on the test. This is more so to get you a little bit more familiar with functions and coding. So shouldn't be too bad. I'll give you what do you call it? A follow-up assignment to assignment 4A somewhere later on. Once I feel that our class is moving in a comfortable direction, I'll feel a little bit better about assigning certain homework. Okay, so that's grading on assignment 4. If we have time at the end, maybe we'll go over the assignment a little bit more into detail. Okay, so that covers all the stuff I want to talk about. And let's go ahead and jump into our lecture topic for today. So today I'm going to try to cover up system calls. We're not going to go through all of them, just the basic input and output, print to console, hello world and all that good stuff. We'll finally be able to execute a program like that. Then what I want to do is talk about a little bit about the 218 horror stories. So if you notice, someone did notice in chat. So homework and tests you can turn in 2 days late with 10% off each day. No, tests you cannot turn in late. Homework and quizzes are not tests. You can turn in 2 days late. I'll open them up an extra 2 days, so you'll be able to submit them. So yeah, it'll be 10% off each day. Not tests. Tests I have to. It takes so long to grade tests. I can't afford to give out more time because then I won't be able to grade everything else in a timely manner. And plus I want to usually cover the test answers the day after. So, right, going back to 218 horror stories. This is a sample assignment 9 that I might have found on the internet. Something that Dr. Jorgensen might give you. And it's roughly around the same time frame. So this is the kind of assignment that you might have experienced had you been taking summer classes with Dr. Jorgensen. So what I'll do is actually maybe we'll go into the assignment and break down some of the coding involved in this assignment just for fun practice. So I'll emotionally scar you with this assignment, but you will not be required to turn something in like this. Okay, so I generally assign about half as much homework, but we try to cover the topics a little bit more in detail with more examples. So it'll basically more or less piece everything that we've been learning together so far, and then you'll see how that works. And then hopefully you can tell by my my expensive cosplay that I am indeed cosplaying as a stereotypical hacker man from Hollywood. So maybe we'll brush up on a little bit of hacking that has to do with some of the stuff we're coding in here. And then if we have time at the end, we'll go over assignment 4. All right, sound good? So let's go ahead and talk about system calls. Let's see. All right, so system calls. So when we, let's say for instance, want to declare a message and print to the console, is a very difficult task, right? So first, let's just define our message that we want to print out. So the covenant hello world. And then we have to have our string being null terminated. Mr. Robot. No, not Mr. Robot. Okay, so if you have this message inside your program somewhere, we'll call it a process, right? So this is your process or your program. Right? So here's the lines of code, and maybe you want to print out to the console. So what ends up happening is, well, we can do in 2 ways. One, we can directly contact the display module. So maybe you'll have a fancy NVIDIA graphics card to display things to your monitor. That's perfectly fine. Maybe some of you have an RTX 3080. That's okay. So you can ask your program to send that information to your display card, and it'll display on the monitor, and then you'll print out hello world on your console, right? Okay, but what if someone like me doesn't have a fancy, RTX 3080? So what happens is if I run this program on my machine that doesn't have this specific display module, then I won't be able to display hello world on my computer. So to bypass that and to make things a little bit more portable, what we can do instead is have it take the lengthier route by sending it to an OS, right? And then the OS should have information about what kind of display card I have or whatever I'm using to display. And it will translate this code into something for my display card to read, and then that gets passed into my console or my monitor to output, right? So in general, the way we have to do system calls such as printing and stuff like that is we have to ask our OS to sort of circumnavigate these hardware constrictions, which is why we don't usually take this approach. While you could do it, it will only be localized to your machine and it won't work on the general machine. So if your TA grades your Hello World program and you have it coded for a specific RTX 3080, your TA is like, well, I don't have that graphics card. I can't do it. I can't display this. He's going to mark you wrong, right? So we have to do our syscalls in order to print out these messages. And now your higher level languages will innately do this for you, but we need to do this in assembly because we're coding everything ourselves. And the reason we do this is because of portability, right? Being able to run this code on several different devices is a practice of portability. Okay. So with that out of the way, now we can actually get into the system calls. So maybe I'll do something like this. Move RAX sys right. OS changes our program to run in the GPU. Yeah, so your OS, right? So let's say you're on Windows 10 or Mac or Ubuntu, whatever, right? Your OS already knows all the hardware that's installed onto your computer, right? So it already has information that, oh, I need to do stuff in order for this specific GPU to print onto my screen. You're such a cool professor. Thank you. Right, so yeah, your OS will handle all of that for you. But there's a little bit of latency, so obviously just directly interfacing your GPU is a lot faster than going through your OS and having your OS do the conversions and stuff for you. But the reason we do it in method 2 is because you'll be able to run that code on any device, or at least more or less any device. Okay. So if we wanted to print out hello world, we'd first have to move the syswrite command onto RAX, and we'll talk a little bit more about your system calls in a second, or like your system operand, so RDI. Now remember how in functions we had our arguments, right? The first 6 arguments are stored into RDI, RSI, RDX, RCX, and so on and so forth, right? Notice how it's a very similar structure here. So in order to call a print command, I know Windows auto-detects hardware to download drivers, but I didn't think Linux did. Do all OS detect hardware correctly? Yes, your OS should always detect your hardware because it needs to be able to interact with all these things. Of course, you'll learn a little bit more when you take operating systems for CS370, or I think it's 370. You'll learn a little bit more about how the OS handles all of those things. We won't get into a lot of detail in this class. I'm mainly just conceptualizing the idea why something like cout hello world has to be done in such a lengthy manner. Okay, so remember that our arguments, when we pass into function, the first argument is passed into RDI. So you'll notice that I will set RDI as my first argument, the protocol for displaying to the console, which are standard out. And then we'll move RSI, the contents of the message. So here, this is the message address, right? I didn't use the brackets to dereference, so this is the address of my message. And then here in RDX, I tell it to print out 11 bytes of information. So in my message, if you were to count hello world, so if we were to just say 1, 2, 3, 4, 5, space is going to be considered a character as well. So 6, 7, 8, 9, 10, 11 is exactly 11 characters. And that's why I want to print out 11 here. Okay. And then we run the syscall by just saying syscall. So remember that RAX, so in general, RAX, maybe I'll write it in a different color. So RAX is the call code. Okay, so you'll use this for syswrites, sysreads, and other call codes that you might need. I think for today we're just going to be only talking about reading and writing. Okay, and then these are your arguments, right? So different syscalls need different arguments. So in this case, writing will require 3 arguments, right? The first one being where to output or write to. The second one is the location of where you want, or where the contents you want to output belong in. And then the third argument tells you how much of that you want to do. So underscore for write, but no underscore for call. So here, these are not actually keywords. What happens is, let's go ahead and bring up some code from Melon World. So if we just throw this off here, you'll notice that these are service calls that are defined. So service calls you can actually replace by these numerical values, right? But you might not remember them all the time, or someone looking at your code might not know that system write is the same as say 1, right? So they might not know that right here, they might not know what this is doing, what move RX1 is doing. So instead, what we do is we can define it as a constant up top in the data section, and so that we can tell for readability what the system call is doing. So this is just one way to define it. You could have defined system write as sys write or some other way, right? As long as you defined it in your constants up top here. You can find the system call numbers in that link. Yeah, you could find them in that link probably. But you can also find them in your textbook. So if we go ahead and pull up the textbook, textbook also has some, I think. Yeah, so here's a bunch of constants that you can call. Yeah, so use whatever reference you want to figure out your system calls. But in general, these are some of the standard constants that we use. We'll be using in this class periodically. Okay, so this is in chapter 13 if you're interested, and there's more notation on things like syswrite. So here, syswrite uses RX to store the operand code. Then we use RDI for the descriptor where you want to output. So in this case, we used standard out. RSI is the address of the characters to write, and then RDX is how much of the characters we want. EQU, remember, is just how we define constants in the beginning of the class. We said this right here is how we defined constants. You know, we really didn't use that a lot in this class. It is not in the code. We did go over that, so go back. So this is the equivalent of something like cout hello world, or wherever the string is, right? Okay, and we did not give it a line feed here, so you can also have defined a line feed right here and said lf and then null, in which case we would have to print 1 extra digit, right? So we'd have to print out 1 extra thing for the line feed. So let's say if we set RDX equal to 5, right? So if we're printing less than, what's the point of syswrite sys std out? Is that the way we do things? So syswrite is telling the machine you want to output something. Std out right here is telling the machine where to output. So in this case, std out just means to output to the console. So going back to our example, let's say if we defined RDX as 5, right? So instead of printing out 12 characters in my string, I'm printing only 5 characters, right? So HELLO. So it only print that out. Okay. And you'll notice if we didn't have the line feed, let's say if we didn't have the line feed, so this is no line feed. When you print out hello world on the console with 11 characters, it will look something like this, and the cursor will end up here. Okay. If we did something like with the line feed, then the output would look like this. So we have the line feed, and then the cursor would end up there. Okay. So one little caveat is in our machines don't actually read, or we can't input on hardware the null. We can't input null anywhere in our hardware. So, which is why null terminated strings is so useful, is because the user can't actually put in the null, but we can use it to terminate. So, talking a little bit more about line feeds. So, line feed usually pertains to Linux, Unix, and Mac, right? But on Windows, we have these things called control line feeds. Or character line feeds. Line feeds on Windows. So you'll notice that, let's say if you coded something in Linux, right? You used like a text editor and coded in Linux, and then you ported that code over to Mac. Let's say the exact same code, right? So maybe in Linux, let's do, for example, you wrote hello world, and then line feed, right? And then maybe hi mom, line feed, and then maybe hi YouTube, line feed, something like that. If we were to go and open that file on, say, like Notepad in Windows, what would happen is it would print out hello world, which shares the same ASCII table, right? So I'll be able to reference that. But then it wouldn't know how to read line feed because it's expecting a CRLF, right? A character line feed. So after that, all your stuff is going to be decoded weirdly because it hit something that it didn't know how to interpret. Now, certain text editors such as Notepad++, they're smart enough to realize that you save the file from Linux and you're opening it inside Windows OS, and now it's smart enough to do the conversions for you, and you can even save the programs. It'll ask you to save it. Do you want to save it as a Linux file or a Windows file? Because it'll tell the editor how to save the LFs, whether to convert them to different line feed structures. So just a little nuance if whenever you do get this jumbled string of mess in Windows. Okay, so we talked about outputting to a console, but what if we wanted to input something? So let's say take user input, for instance, right? So if I'm expecting user input, might be good to have something to store my input, right? So maybe we'll store it into a character. So mychar, very creative variable name. Let's just initialize it to 0. I don't have anything to put in it yet. Okay, so then to do that, all we have to do is call the system code for it. So So sys read, and of course you would have to define the const for this somewhere in data. RDI std in, so that's telling you want user input. Of course, you also have to define what std in is. Then we have move RSI, the address of where I want to store the value. So I want to store the value in my char. And then I tell the machine how much input I want from the user. So in this case, I only want 1 character byte. And then I'll call the sys call. Okay, so this is one byte input. And this is the address to store. And then this is where input comes from. And in this case, std in is equal to user input. Okay, so maybe in the future, you'll ask it to grab it from a file. Remember that console inputs, consoles are also treated as files, so that's why it's appropriate to put standard in the file location. Okay, so before we go into maybe storing more data than just a character, I should do a quick little tutorial on dealing with uninitialized values that we've never really touched up on until now. So in the BSS section, remember we talked about this for the uninitialized data. It's very easy to declare it. It's very similar to how you would a normal value or a normal variable. So you start off with the variable name. Then we go to the res type. Okay, so how much you want to reserve. And then we go into the count. So the amount you want to reserve of that type. Okay, so that might seem pretty unusual, but let's go ahead and talk about the different res types. So res types we have is, let's see, res types, and then this is the size of that type. So remember how we had we had like DD, DW, DB, DQ, and so on and so forth. Well, for same thing for res types, we have res B, so reserve a byte size, so that would be 8 bits. Res W for word, or 16. Res D for 32. And then res Q for 64. This one we probably won't be using this class foreseeably, but this is for 128. Okay, so to kind of declare this, right? Let's say for an example, I wanted to do a byte array, an uninitialized byte array. I can say B array is equal to res type of byte, so B, and I want 10 of these. So this is saying that I want a 10 element array, and each element is going to be a size 8, right? So this is going to be 10 element, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 10 element array, and each one is size of a byte. Okay, so BR, that's what it ends up being. Okay, and there's 10 of these, so this is the 10th byte. So let's go, for example, let's do word array. So res W this time for size word. And let's say I want to declare 50 of these. So I'd get 50, array of 50, and each item in my array is size word, okay, or 16 bytes, and so on and so forth. So maybe a D array. I'm not going to draw the array for 50, but you get the point. So let's say maybe I wanted 100 items, and then maybe for quad array, let's say I wanted 200 of, right? So this would be a 200 item array of size quads. Okay, so hopefully that's not too difficult. But the reason we need an uninitialized array, for instance, may be because we want to store user input in one, right? So perhaps instead I can, in my BSS section, define something like my string, and I want the string to be a byte. So each item is a byte, and then I want a length of 5. Okay, so this is basically saying a string size of bytes with 5 items. So just remember that the uninitialized part, right, says if that's reserved, if that's your code, so your text, this is your data, and then your my string will be somewhere here in your BSS section. Okay, this is just a visualization of memory. All right, so maybe we go ahead and start coding what a read input for more than one character would look like. So let's say we have move rex, then we do a sys read again. Maybe we'll do a move RDI, standard in, because we want user input. Then we do a move RSI, so how much or where you want to have it. So in this case, we want to store it into my string, so my str. Okay. Then we have to move RDX, how much bytes you want to use or store with. So in this case, we want 5, right? And then we do our syscall. Okay. So maybe we'll do some examples of what user input might look like. So let's go ahead and maybe segment this. Internet connection. Okay, let me see if my internet's back up. Okay. Hopefully everything's back up. Enjoyed your stay. Yeah, hopefully everything is back up. My internet had a slight hiccup, so it did unfortunately end the stream, but the recording is still going on. So I refreshed the page thinking it was me. No, it's all it's all of you that are having the problem, not me, not my internet. Couldn't be. Okay, so hopefully the stream is back up at this point in time. I have construction going on home that I knocked out. Oh my god, I disconnected again. Okay. So that's unfortunate. Okay, hopefully the internet doesn't go down again. But if the internet goes down, I'll just resume the recording, and then I'll try to just reteach it in session 2. So I'll just keep trying to relaunch the stream, but I'm just gonna keep going through the material and post the recording, if anything. Okay, so what ends up happening is let's say our input is A, B, C, D, E, right? So let's say example input is A, B, C, D, E from the user. Ads? Oh no, not the ads. I'll just go relatively slow and just set up the example. But looks good now. Okay, we're live. Excellent. I'll have to complain to my ISP later. But here's our example input from a user. We get A, B, C, D, E, and then we will store this into the myString address, right? And that's what it would look like. Let's say, for example, the user decides to 2, 3, 4, 5. The user decides to input just AB and then terminate it with a line feed or the enter. Welcome back, everyone who had to unfortunately sit through ads. So what happened is we'll just get AB line feed, and then that will terminate. Since there's no more user input, these don't actually get filled in. Let's say if the user, because we don't have any thing to stop the user from doing this, let's say we do A, B, C, D, E, F, G, H, I, J, L, M, N, O, line feed, right? So what happens here is actually quite interesting. So our buffer size or our array size, so you'll hear these terms kind of being interchangeable. So first thing happens is it'll read A, B, C, D, E, and it'll store A, B, C, D, E. But then since your input never stopped, we're going to have a buffer overflow. And what happens is it will go back to the beginning and overwrite these next values with the next 5 characters. So F, G, H, I, J. And this concept will come back to haunt you somewhere down the line. So, and then the last bit, right, gets overwritten by K, L, M, N, O. So your string now has the last 5 bytes of data. So this is what we kind of call a buffer overflow. This will come back when we're discussing about how to hack people's programs. Okay, instead, maybe we can try to circumvent this buffer overflow by only reading, say, a character at a time. So instead of reading 5 characters at a time, maybe we will just try to read 1 character at a time. So again, maybe let's set a new variable. Let's go ahead, go back with myString, call it res b, and then declare size 50. And then now we'll bring in mychar, which now is res b of size 1. So here's my array of 50 to make a string. Can you go over the second example? Where will it haunt you? Well, it'll haunt you because if you commit this buffer overflow crime, your program is susceptible to getting hacked. But we'll go over that in the hacking section later on when we do some coding. Okay, so second example right here. So we have our array of size 5 items, 5 bytes, making up a string. We call our sysread very similar syntax to syswrite. So call the read operand. We call the code for standard in, so user input. We give it the address of my string, so this is where I want to store it. And then here is the amount of input I'm looking at a time. So if the user inputs 5 items or 5 letters, right? So A, B, C, D, E, that's all fine and dandy. It all fits into my array. No issues there. If the user decides to put in less than that, so here's my line feed telling me that the user just ended their input without filling the entirety of the buffer, it'll end up looking like this. And then in the last example, the user has given too much input. So what happens to the buffer is the first 5 letters get put in, then it's still reading in input and has nowhere else to go, so it has to go back to the beginning and override the buffer or the array with the next 5-letter content, and then one last time for the last 5 letters. And this is what we call a buffer overflow. And this concept will haunt you if you don't appropriately deal with it. And that's what we're going to go over next, is how to stop buffer overflow. We'll go a little bit more about why it's bad, other than just wiping your data in your buffer. So the last 2 boxes are empty if the user inputs less. Yes. So the first 2 store A and B, which was the user input, and the user also inputted a line feed. So we got to put the line feed there, indicating that it was the end of the input. Okay. So let's go ahead and talk about how to deal with buffer overflow. So let's say here we redeclared our variables a little bit differently. This time we'll have a buffer size of 50 for our string, and a same thing for our character. It's only a size of 1 because we only want to look at 1 character at a time. All right. So maybe what we can do is first, let's go ahead and move the address of my string. So maybe we'll do my string. So this stores the address of my string in there. And then maybe we'll initialize, say, R12 to 0 for a running index. Okay. Okay, so maybe let's go ahead and try using a loop this time. So maybe we'll do a read next. Okay. So we're going to call our system stuff, right? Let's go ahead and maybe do like the move RAX sysread. Then we do move RDI standard in. So now we're getting input. And then we can move, say, this time I want to be storing the input inside inside mychar, right? So the address of mychar, let's go ahead and say RSI mychar. And then let's go ahead and move RDX, and we only want to look at 1 value at a time. Oh, man. You bought it like crazy today. Okay, so just the standard. So this code right here will read in 1 character at a time. Okay, so the no should not experience overflow there. Okay, so maybe we want to store the character now. So let's go ahead and move R10D bytes. Bytes. So now I'm storing, so I'm dereferencing where mychar is, and mychar contains the value of the input. So now I pass mychar into a register. Then we can compare to see whether R10B is a line feed. So line feed has to be previously defined, right? LF is defined already. Just assuming that these are all also defined in your constants and data. So you compare it to a line feed, and then maybe we do, if it's equal to, then we're done, input done, right? So we'll jump to input done. Otherwise, what we might want to do, right? So jump if line feed, implying that no more input to read. And then we'll move otherwise. So this is move byte RBX, which is the address of my string. So from the address of my string, I'm going to update it by my index. So my current index is at 0, so it was just be the first index of my string. I'm going to move the contents of R10 in it, so otherwise store my char into my string plus index, right? Or my string at index, right? So this is kind of like C++. You would put your index in there, and then we increment our index, right? So increment R12, and then let's jump and force our jump back to the read next instruction or the label. So go ahead and do this loop until we terminate by line feed. So it's a while loop terminated by a line feed. You can think of that. And then let's say input done label. And then the last thing we have to do is terminate our string by adding rbx plus R12. So this is the last part of the string, and we need to terminate it by a null, which is also defined in data. Okay. So hopefully that now we kind of solve our buffer overflow problem, right? Because we're only adding one item into the string at a time and not a sequence of 5 or more that can overflow the buffer if we're not careful. Okay. And maybe you want to do a little bit more checks and conditions in it. That's perfectly fine. But here's more or less how you kind of avoid that by just reading one character at a time. Okay. So hopefully input and output is not too difficult, but now we can appreciate things like cout hello world, right? Or maybe even cout string, right? My string. My string, right? So something like this, our compiler does very nicely for us and breaks it down into a bunch of assembly code. All right, so any questions on system calls for input and output? So let's go ahead and bring up Melon World again. Right, so here we've defined all the system services we need. So the other system service for returning out of the code, right? We need the success one, but we have center out and we have syswrite, and all this one does is it will print out this string right here. So we can replace line feed with LF had we defined it as LF. Doesn't matter what we define it as. And then this, just looking at this, right? So we move the system operand here, the case write. Where to write it, we want standard out, the string address, the string length, and then we just call syscall, and then the system will do all of that for us, and we'll print Melon World into our console. Here to end the program, ending program uses the system exit protocol, and all you need to do is pass it success, and then you call the system. So essentially, this entire block of code is equivalent to cout, that string, end L. Well, there's no end L unless we have a line feed, but yes, essentially that is that 4 blocks of code right here is cout, melon string. So if we wanted to write this in C++, it'd be cout, melon string. Right? Do I have a line? I think I have a line feed melon string. You could put the line feed, I think, in the string, or you in C++, or you can use end L for that. That will also work. So yeah, that would be the equivalent of that. So it's a little bit more involved, which is why on day 1 we weren't able to do very complicated programs such as print to the console yet. since we had to go over functions, since it does use the argument stack that or like the argument calling convention that we had discussed about last class and the class before that, we needed to know how to deal with registers. And then we have to learn a little bit more about some other things before we can do this. But now you're able to print out things for your homework assignments. So maybe that'll be a little bit easier. Maybe you'd like the debugger. Who knows? But hopefully, at least now we can learn or have learned how to print to the console. A very sophisticated routine. And of course, an input loop is even more sophisticated if you want to avoid the buffer overflow problem. And I'll talk about a little bit more into why the buffer overflow problem is problematic. Okay, but first, before we can talk about how to hack into, say, a system, maybe we should talk about stack dynamic variables. Ooh, fancy words. So stack dynamic variables. So remember, in a function, let's say some arbitrary function that we have defined, we if that's proper syntax. Let's just say we have something like int a, b, c, int array size 10, 100,000. Let's go 100,000. Sure. And then some code, and then whatever, right? Maybe it's a void function, maybe it's a return function, doesn't matter. But you'll notice that these variables right here belong only to the scope of the function, right? These are what we call our local variables, right? Because they only belong and they can only be referenced inside where they're called from, the scope of where they're called from, right? And the reason for this is because if you look at it in terms of stack dynamic variables. So what happens is when the function is called, right? So when called, space on the stack is allocated for them. Okay. And then on exit or return, right? What happens is they will be deallocated. So they'll be removed from the stack. And that's why we can't access, say, variables ABC inside our main function because they're not local to main. And by the time you leave that function where they were defined, they're no longer on the stack and you can no longer reference them. So quite similarly, what if we had also a function 2, right? And maybe we have another array. Let's call it array 2. Jesus, I'm being rebotted. Crazy. A lot more than usual, but okay. So ban those bots, and then we declare our array 2. So let's go ahead and declare this as well. Okay, so if we were to look at this, right, this function, this array, would use up, say, 4,000 bytes, right, or 400,000 bytes, because each integer will take up that much, 4 bytes, or 4 megabytes of data in our RAM. So this operation gets quite expensive, right, if we don't deallocate our variables from the stack. Same thing, right? So if I have another function here, what's nice about it is if my function doesn't, if I leave function 1, then I don't need the function 1 argument or function 1 variables on the stack. They get deallocated, and then that can be used for function 2, right? So if I in main invoke this, so in main Maybe we have call function 1, and then we call function 2, right? This will allocate 4 megabytes of memory, but then deallocate, so it's fine. And same here, right? But what if I invoke function 2 in here, right? So what happens on the stack is, here's the stack, right? We have all the registers and stuff put in. RP gets pushed on the stack when I call it. And then somewhere on the stack, I now have my stack dynamic local variables, right? And then if I call function 2 within my function 1, then I get another standard calling convention, and then function 2 stuff will be stored into here as well. So I'll be occupying 4 megabytes here and 4 megabytes here. And then until I'm done with function 2, I don't deallocate any of this. Okay, so if you're chain functioning, it gets pretty expensive in terms of memory usage. Okay, so let's look at the standard calling convention for having stack dynamic local variables from functions. So this is the standard. So hopefully by the time you're done with 218, you'll understand quite extensively how things are put into memory, how they're used, how they're referenced, why you can't use variables from other functions if they're not in the scope of your function. And it's all due to how memory is managed using the standard calling convention, so on and so forth, right? So let's go ahead and look at our memory. So remember that this is maybe some stuff on the stack prior to the function call. Remember that if we passed in arguments 7 plus, they get stored on the stack. Then we push in RIP, then we push in RBP, and remember that we set RBP equal to the current RSP. Okay, so now RBP points here. And then our stack dynamic locals are going to be here. Right, so our stack dynamic local. So anytime you declare a local variable in a function, they will get pushed onto the stack here. Then maybe your registers that you save, so RBX, R12, and then maybe RSP is pointing down somewhere down there. Okay, so these are your reserved registers, remember? Reserved registers. So the only new part that we've added to this standard calling convention is this chunk of memory that is allocated to save your local variables. And then we can also talk about how to access them, right? So remember that the base pointer is a reference between the stack dynamic locals and the arguments that are on the stack. So remember that RBP plus some number, let's use n to denote some variable number, will access stack-based arguments. So these are the arguments that get passed from your caller routine. Okay, as long as you have 7 or more, they'll be called from they'll be put on the stack. Okay. Remember that you have to increment, so that this is 8 and this is 8, right? So this starts at least plus 16. So if you wanted to access some more stuff up there, you might have to increment more as well. And now RBP minus some number, we'll use a different variable since the numbers aren't identical. These are the stack dynamic locals. These are how you would access your local variables in your function. Okay, so hopefully nothing too bad. So since you already had experience accessing arguments on the stack, accessing stack dynamic locals on the stack just by decrementing RBP should just be more or less the same, except you're going the opposite direction. And of course, you'll be needing to know how much to get to these. But of course, you can always just pop things off the stack and get back there. Okay. So, with that said, now we can bring back some horror stories from 218. Then I don't know if I'll be able to finish the whole thing, but hopefully we'll do a little bit part of it so we can see. So this image is very blurry, and I can't really read everything on that. So what I've done is I've taken the liberty and converted it into a nice PDF. Just retyped everything. Okay. So here's a sample assignment that you probably would have done around this time had you been taking this course with Dr. Jorgensen. I think his homework assignments are actually very intricate and elaborate. So let's go ahead and look at what a sample assignment might look like. So first off, he gives you a C++ main program that will call some functions, right? So your job is to create functions cocktail sort. This will sort a list of numbers into ascending order. Okay. Sample stats. This will find the min, the median, and the max for that list of numbers. So obviously it might be easier to sort and then to find the median. iAverage will just return the average for a list of numbers. Variance computes the variance and returns the variance. And then this is what we'll cover over today. So in addition, he wants you to write a function that reads ternary numbers that will read a ternary number. So I think that's base 3, if I'm not mistaken. Base 3 in ASCII format from the user. The routine will use a system service for reading data from the keyboard into a buffer. Call a routine to convert the ASCII input from the buffer into an integer, then return the integer. The number must be between 0 and max, defined constant. The function should reprompt for invalid or incorrect input. And then when the end of the input is received, then you should return a no success. So, and then it also says all functions should use a stack for local variables. No static variables should be declared, so no globals. All provided data items are unsigned integers, and then that's how you would do it. So let's go ahead and just concentrate on this part of the function. So maybe we'll code a little bit today just to kind of tie everything up together and make sure that all the concepts are adequately referenced and utilized. So instead of having flashback nightmares to 218, I will be the one to kind of guide you through the process of maybe doing one of these assignments. Okay, so let's go ahead and interpret the function, right? So first, if we're looking at the function, use not pink. Let's go ahead and say read. I'm just going to say tnum because I don't want to rewrite that function name over and over again. So read tnum. This basically the algorithm for this, right? You need to do a few things, right? First, we need to read user input. So this is stuff we covered today, which is very nice, ties in very nicely. Next, we have to check the format and convert it, right? Probably won't go into this extensively because that's a different algorithm from a previous assignment that he also covered. So we'll just call a function to do this. Check range is pretty trivial, right? We just have to compare our result, make sure it's between 0 and the max. And then the for is to just return the value, right? Okay, so primarily we'll be concentrated on this part because this pertains to us a little bit more. So a arbitrary algorithm for this section might look something like this, right? So maybe in we'll do like a read next, right? Just like we did earlier. So we want to read some character, right? And then if it's a line feed, right? So if the character equals a line feed, we need to exit the loop. Then our string with some index I is going to store the character otherwise. Maybe we'll need to increment our index. And then maybe we'll say we need to jump to the start, right? And just continue the loop. So keep looping until you read the next input. We maybe have a exit loop here. And then remember we have to append the null to the string, right? So, and by the time we call this jump, or by the time we exit, we are already incremented our index. So the next character being null should be fine. Okay, and then after that, obviously, we'll do the check function, and then maybe we'll check the range. Maybe that's another function, and then we'll return, right? So remember that whatever we store in EAX or the A register gets returned. We won't cover these since they're a little bit more involved. I'd have to teach you ternary and go through an algorithm for that. So we'll assume that this was already coded somewhere and we can just reference, no big deal. Okay, so let's go ahead and dissect this a little further. So in his main C++ code, or for his assignment, he mentions that he wants to also append an error message. So if the user messes up, then we have to print an error message and tell the user to reprompt the user. So somewhere we need to define the error message, and that's equal to error enter with an underscore. Okay, and then it becomes null to terminate. So we know that this is roughly 17 bytes of value, like byte letter values, and then we also have to append the nulls for a total of 18 bytes in this string, the print string. Okay, so we need to store this as a stack dynamic local. Okay, so maybe something we have to consider is, well, first of all, maybe we need, so if we're looking at our stack dynamic local, right, on the stack, so this is where your SDLs are. Maybe, like, again, we'll use a myString, and maybe we'll use 50 for our size of myString. Maybe we'll need mychar, right, which is size 1. And then maybe we need size 18 for the error message, right? Okay, and this is 18. So when we allocate our stack dynamic locals, we're going to use 50 plus 1 plus 18, which is 69 bytes that I need to allocate before I can use my stack, right? So before I can push other things onto the stack, I need to allocate 69 bytes for my standard or my dynamic locals. Okay, so just something to keep in mind. All right, so let's go ahead and maybe code this just to show you what some sample code might look like. So let's go ahead and start with our global declaration. So read tnum, okay, and then our label for it, read tnum. So remember, it's if we're accessing stack dynamic variables, we need to, not stack dynamic variables, stack-based arguments, we need to push RBP, and then we need to set the current RBP with our current RSP. Okay. That's just a standard calling convention. So nothing new here. What's new is now we have to subtract the RSP by 69 bytes. So this moves RSP down 69 bytes. And we chose this number very specifically because remember when we said how much room we need to allocate for our SDL, we said it was 69 bytes. So if we were to go back here, you'll notice that this number is significant because in our stack, so here's maybe RIP, here's RBP. So current RBP is pointing here. We might have stack arguments up there, might not. But what's important in this example is that we're going to be allocating 69 bytes for our stack dynamic locals. Okay, and what we said was 50 of that goes to the buffer, so the string buffer. 1 byte goes to the character buffer, and then the last one is the error message, right? The last 18 is our error message. So at this point, this is 69. This point is 51, and this point is 50, right? Assuming this is 0 in reference to where RBP, the address of RBP is. So an RBP pointer. So what we did was now we updated RSP to point here, because that's the old RSP plus or minus 69, right? And then let's push any registers that we might use that are preserved. So maybe we used RBX, maybe we used R12, and maybe we used R13. You don't have to push these if you don't use them, but right here is push reserved registers if used. So push RBX, push R12, push R13, and this is where the new RSP is. Each SDL is on a 64-bit register. Okay, it's not. No. These are not registers. So notice how 69 is not a divisible number by 8. So you would not be able to fit these in the conventional register. So when we push and pop, the items must be 64-bit. But that doesn't mean we can't update the address by bytes. Remember that memory is byte addressable. So I can access any segment of memory by increments of a byte, right? So in this case, I am able to allocate 69 bytes to put into in memory for my SDLs, okay? But when I use the push and pop commands, notice that I'm pushing in 64-bit registers because that's the convention we have to use for accessing the stack like that. So for RSP, because these commands, remember that these commands push or change RSP by values of 8 bytes. That's why we need to push and pop by 64-bit operands. Okay. So maybe let's also make an assumption that, let's say, one of the arguments was an RDI, right? So maybe some argument was passed in RDI, right? Because maybe we have stack-based arguments, maybe we don't have stack-based arguments, but we know RDI is the first argument that gets passed in, so chances are it is an RDI. So maybe what I can do is just store the value of RDI because when we do a syscall, syscalls usually will mess up my RDI register. So what I can do is temporarily save it into a different register. So so maybe this is maybe store contents of RDI. I mean, you can also like push RDI onto the stack and preserve it that way. There's multiple different ways that you can do to save your register values. But in this case, I just chose to copy it into a different register that I might not use. Okay. So I will teach you one little thing that I haven't shown you yet, and that is the LEA command. So off to the side, we'll just write. So usually, if we do something like move RDI byte RBP minus 69, this right here would store whatever is in the 69th index from RBP. So in this case, it would be null, right? Since it's terminated by null. So here, the 69th one is null. So I would be storing null into RDI. But if I use the LEA command instead of the move command, this will overwrite that and say, no, I just want to store whatever this address is, right? At RBP minus 69. So this will actually just store address of this. Okay, so it might be useful when we're trying to navigate through the buffer and extract certain things. Okay. So next, what we have to do is initialize our stack dynamic variables, right? We didn't actually code this error message, or was it? We didn't actually code this error message yet into our stack or into our function variable, right? So we still need to store this onto the stack to use. So what we can do, so now we need to store the error message into SDL, right? My stack dynamic locals. So what I can do is maybe say move dword, or let's do the long way first. So move byte. What is it? RBP minus 69. Let's say we want E. Sorry, this is not null. This should be E because we're working bottom up. So if we were to look at memory, we would want negative 69 E, then R, then R, then O, then R, and then so on and so forth. Okay. So I could just say move the character E into RBP minus 69, which is this address here. And then I can do that for R and so forth, and that would take about 18 lines of code to do. Or what I can do instead, so let's comment that out. Instead, I can move it by different sizes, right? So I can use a quad, which would probably be the most efficient, but for now, I use dword just to show you that it can be done in any size. So dwords are 4 bytes, so I can store 4 letters, so ERRO. And then the next one I would do move dword RBP, and now that I've updated by 4, I'm at address RBP minus 65. Then maybe we'll do R, comma, then we have a space and then R, right? So that's 4 characters there, and that'll give me my next 4, and I'll do that until I finish it. And since 18 is not divisible by 4, we're going to have the last 2 as bytes. So move byte RBP minus so it ends at 51. So at 53, I should have my second to last byte, which is what was my error message? Error message was R 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 17. actually it's colon and then null is the last one. So colon is my second to last, and then move byte RBP minus 52, and then we put in null there, and that will give me my error message. So here's the colon, and then here's null, and that's all in my stack dynamic local right here, where it says the error message. Okay, so that's how you would initialize that. So that was the error message code. Now maybe we want to do the input. And I think I'll only have time to talk about the input. So maybe we'll go over hacking and buffer overflow tomorrow. I probably won't wear the same cosplay since it is scorching hot. But let's go ahead and finish off with the read character code. So here, I'm going to use the new fancily defined operation called LEA, and I'm going to store the address of, say, RBP minus 50. So remember that this is where my buffer would start, right? Because my buffer starts at index 50, right? Because the character, oh, this should be 50, but the character starts at 51, and my buffer, or my array, will start at RBP minus 50. So this stores the address of SDL buffer. Okay. Again, we'll move R12 as 0 for my index. And then we'll move RAX as the sysread. Then we'll move RDI as the standard in. Then we need the address of where to store the character, right? So again, I'll use my LEA instruction. And this time, remember the character address, I want to store it in the 51th byte from RBP, right? So 51 is where the character will be stored. Of course, you don't have to store it in this order. I'm just doing it in this order. It's 1, so I only want to read one character. Then we do our syscall. So that reads in a character. And then we do the move R8B. So this is a register that is not reserved, so I don't have to push it. RBP minus 51, so that is where the current character is stored. And we compare with line feed. So if it's line feed, we exit. If not, we don't. So jump equal, we'll just say input done. So in done, and then I'm running out of space. We need to store, otherwise, the input. So we don't want to store the line feed, but we still want to store if it's not a line feed. So move byte RBX plus 12, my index, and then I want to store the value if it's not a line feed. I want to increment R12, and then let's just move over here. I'll do a JMP, so maybe we'll jump back to the read character. So let's make this a label, actually. Otherwise, we will skip that and say in done, and then we have to terminate our string with a null. So byte RBX plus R12. So before this should already be updated before terminating. So it's safe to just slap the null on. So this is very much like the code we did earlier over here. No, one more. It's very similar to the code we did here, except I threw that into our function. Okay. So hopefully that is more or less how to do that part of a potential homework assignment from ACS 218 class. Or at least the input part, reading the input part. Okay, so is there any questions about the horror stories from previous classes? Questions on input and output and the stack dynamic locals that we covered today? So obviously, a little bit more involved with more addressing. That's why I think yesterday I spent a bit of more time giving you more addressing examples. That way, you'll feel a lot more comfortable using SDLs and stack-based arguments when we go to functions. Make it go away. Yeah, just hopefully you have newfound appreciation for your compiler. Can you scroll down for a bit? Yeah. Do you use a mechanical keyboard? Yes, I do. I have a Armilo Cherry Blossom Edition with Rose version 2 switches. Here's. Okay, so hopefully that's all fine and dandy. I'll just quickly discuss assignment 4, and then I will let you guys go. So here's the calling routine. So I want you basically to code the calling routine that will call this function. So you're going to have to assign your registers in this order. You need to push some stuff onto the stack, call it, and then update your will test 2 be next Friday? Yeah, test 2 would be next Friday. Yeah, slurring everything. So yeah, you'll have to push in some variables. So I think G through J you'll have to push, and then you'll have to update our RSP once you're done calling the function. And then question 2 is to write the actual function itself, and you want to basically calculate the average of all of these numbers and then return that in RAX. And of course, you got to follow all your standard calling conventions. So it's more or less to help you get comfortable because I think averaging something is pretty simple. It shouldn't require too many operations. But it's mainly to get you used to touching things on the stack in functions. Okay, so it shouldn't be too hard. Should be easy 20 points, which we can quickly use a calculator and figure out. 20 divided by 48. It is roughly. Is that right? No, wait, that's too much. So I'm off by. No, that's correct, right? Yeah. No, I'm off by 10. So this is roughly worth. It's roughly worth 4% of your grade. So make sure you do it. Okay. That said, is there any questions about today's topics? Percent correct. That's a lot. Okay. All right. Well, if there's no questions, hopefully, if you're struggling to keep along with the lecture, just follow the notes and maybe rewatch one of the VODs, and hopefully it'll start clicking because we're going to start tying a bunch of concepts together So if you're not comfortable with certain things, make sure you brush up on that. Other than that, I will see you all tomorrow.